the study of trigonometry can be quite convoluted, as trig is as present in our nature as other elements like air and water. Specifically, it's the study of the relationship between the angles and sides within a triangle and how they change with each other. It's often the case that students wonder about the use of trigonometry, since it's typically reserved for higher mathematics like calculus and can be a pretty abstract concept if you're not doing anything precise. So today, I want to walk you through 3 examples of how we use trigonometry as engineers to further your appreciation of the subject. First, I'm going to introduce you to something called field-centric driving, a principle highly applicable to robotics, such as the robots used in the first tech challenge competition. Consider this problem. If our robot is tilted at an angle, where should it go when our driver presses forwards on the joystick? To preface this, I'll state 3 things given our environment. You can get the coordinate of the joystick as x and y coordinates, and the sums of the squares of both coordinates are bound to the domain and range of -1, 1, inclusive, forming us a nice unit circle. Your robot will always know its relative heading displacement from when it started up. This is because of a nifty little sensor called the inertial measurement unit, which can measure and store rotation through inertia. And the robot is holonomic as opposed to a standard differential drive. This means that, unlike your car, you can move in any direction without having to turn, giving us omnidirectional movement. There are 2 main possibilities to consider. The first one, we'll call that robot-centric, is very similar to driving any old RC vehicle. When you press forwards, the vehicle moves in its frontal direction. However, in some cases, we want the driving to be more intuitive, and so instead we want to use a method called field-centric, where the vehicle moves in the direction relative to our global frame of reference, regardless of its orientation. This is very useful in high-octane situations like competition, and also applicable in cases where you might want the robot to follow a path. To accomplish this, we can take our joystick coordinates, x and y represented in a column vector, and multiply this by a rotation matrix. I'm not going to go over the exact math for this, as 3 Blue 1 Brown has an excellent series on linear algebra. What we end up with is a vector that's been linearly transformed to rotate our input command to compensate for the robot's orientation. Now, I'm going to remove the braces. Take a sec to think to yourself, do these 2 equations look familiar at all? They are in fact the angle difference formulas. The missing cosine and sine functions are those of the joystick, but they're actually embedded. Let's think of the angle that the joystick is being tilted at as alpha, and x and y as the coordinates of the joysticks. No matter where the joystick goes, x and y are related to alpha. You might recognize x as the cosine of alpha and y as the sine of alpha. Therefore, we can actually go back to the elements of the transform vector and substitute cosine alpha for x and sine alpha for y. And now, we have the angle difference formulas. Intuitively, this new vector doesn't seem very useful, but now, let's show it in a linear transformation. Since our robot was offset by 90 degrees counterclockwise, we're going to be taking our vector and rotating it 90 degrees clockwise to compensate. The result of this operation is a modified command that we feed into our vehicle. If we use our robot's orientation, you'll see that we're tricking the robot to move to its right, which would be our forwards. You can repeat this for any orientation on the robot, since the rotation matrix will always change based on the robot's IMU reading. The result of these operations done over a continuous period of time is smooth driving that is intuitive and adaptive for the robot operators. My next example is of delta robots, most commonly seen in 3D printers and other industrial applications. The way these machines work is by having 3 arms with flexible joints hold up a lightweight tool head, which makes them extremely fast. These joints are attached to both the tool head and a linear rail system that moves them up and down with belts. The process of computing the position of a delta robot is known as trilateration. Let's take a look at one of these arms, represented in this right triangle. Since the hypotenuse is fixed by the length of our physical arm, we can figure out the height of our rail carriage above the tool, and how far our arm will extend out in the direction of our tower. Since we will more often work with how far we want our arm to extend, we'll work with the bottom base and use the Pythagorean theorem to solve for the missing height. If we label A as the distance from the toolhead to the pillar, and C as the hypotenuse, we can then solve for B by taking the positive square root of C minus A squared. We're using the positive version since we're hoping that our arm never angles upwards. Add that length to the height that we want our toolhead to be at, and we can command our carriage to rise to that position. And now, with some more linear algebra and a few cross products, we can solve a system of equations to see when our arms will intersect, forming the position of our toolhead. Remember that our arms can be at an angle, and their distance is controlled by the height of each individual arm. All of this is automatically controlled by software. One of the most popular 3D printer firmwares is Marlin, which has a few delta functions. Don't worry, I'll walk you through the code even if you're not familiar with C++. You'll see that not only are trigonometric functions used to find the exact x and y positions of the towers in the circular base, the Pythagorean theorem is used to calculate the coefficients for the height commands based on the unit triangles. Many of these variables correspond to different settings of the printer, but the most notable one is delta diagonal rod, which again was the length of our hypotenuse. Again, solving the system of equations is not covered in the scope of this video, but I'll link the firmware in the description if you're interested. Finally, I had the privilege of speaking to Mr. Andy Bourne for my last example. He's a technical fellow at Boeing and has helped pioneer the GPS system we use today by working on the US Air Force GPS program, as well as the Federal Aviation Administration's Wide Area Augmentation program. He gave me an in-depth look on how to calculate a position given 4 GPS satellites and a receiver. Before we begin, it's important to know that each satellite can already calculate its distance to any receiver within its view on Earth. This is done using a methodology known as radio time of flight. Because the speed of radio waves is constant, about 300,000 meters per second, a satellite can send you a signal and measure the time it takes to travel and come back. Satellites have very high precision atomic clocks that can measure up to a billionth of a second in time difference, which may seem high until you realize that radio waves travel to and from the receiver in less than a second. Then, the speed is multiplied by the travel time divided by 2, since we're doing a round-way trip, and the distance is calculated. Satellites use this distance to draw a sphere around themselves in 3D space, where the receiver can be anywhere on the sphere's surface area. While this may seem incredibly pointless since there's an infinite number of possibilities of the receiver's location, it becomes much more useful when we have multiple satellites pinging the receiver's position. This next part's a bit harder to animate, so I'll show you directly in some 3D modeling software. Let's say that this red dot is you on the Earth's surface, and this pink sphere represents the distance of one satellite. As soon as we add another satellite, our possibilities become a lot more limited. When we take a cross-section view, you'll see that our possible positions have shrunk to the range of the circle formed by the intersection of the pink and green spheres. If we add a third satellite, you'll see that now we're confined to 2 positions, both on the same axis, that intersects the center of the Earth. Finally, once we add a 4th satellite, we know for sure which of the 2 solutions we're at. Now, it may be hard to understand where the trigonometry comes into effect here. However, if I put every sphere into the same position, you'll see that we once again have infinite solutions to our system of equations, since every solution resides on the same sphere. To counteract this behavior, we can use the law of cosines to figure out each satellite's angle from the receiver, labeled L, and later use that in our 3D projection to solve our system of equations. For each satellite, we need to know a few things. We need to know the satellite's radius, known as rs, the constant of the Earth's radius, known as re, and the distance d from the satellite to the receiver. Now that we have 3 sides, we can plug them into the law of cosines to solve for L. We'll start with the common form of the law of cosines. D equals the square root of re squared plus rs squared minus 2 re rs cosine L. From there, we can square both sides to remove the radical, and then move the re squared and the rs squared to the other side of the equation. After that, we can divide everything by negative 2 re rs to isolate cosine L. Finally, to reverse cosine L, we can take the arc cosine of both sides, which will give us the angle of our satellite that we can use to compute our intersection of 4 spheres. Adding a footnote to this point, since you saw how when we clumped the satellites together, yielding a very low accuracy, we want our L to be as big as possible, and or to sample from as many satellites that are spread out as we can. What this will do is increase our tracking accuracy, since large differences are magnified over greater distances. This is just some of the work that Mr. Bourne did, as he worked to calculate the GPS accuracy on 15,000 points on the globe. The yellow regions of the map yielded the highest accuracy, roughly 2 to 4 meters within your position. The light blue region is average, 4 to 6 meters, and the dark blue regions have the lowest accuracy. These low accuracy regions have very few intersecting satellite orbits, causing fewer satellites to be in view at a given time. That brings us to the end of our video. I hope it was helpful in understanding various ways that trigonometry betters our society and why it's important to learn the subject. If you're interested in learning more in the related fields, I highly recommend you pick up some linear algebra and differential equations to solve those systems of equations I mentioned earlier, or take this knowledge with you to calculus. Good luck on your math journey!